then your Face ID
Do they
scanned,
do they
and
measure your
they
bone density as well, or
yes, yeah, they
yes?
do the whole thing. Your teeth, your retina scan. No, but when I went back, hey, dude, when I when I went back, it was a lot easier. So you get to stand in this other line to basically get back through customs. So
Yeah, yeah.
we'll see.
That's what
But
happened when I got the green card. It was easier for me to go through the airport as well, so it was all worth it.
yeah, Ethan's telling me when he came to the U.S. for the first time, he had to get a full
Not for the first
examination.
time. I've been to America 10 times. That's what I'm saying. This is how
Uh,
ridiculous the thing was. But in order to migrate there, I had to go to the embassy and get a full physical. Part of that physical was letting a doctor put something up my bum. And when I say something, like, his finger in a glove.
but you got your green
You,
card. That's
I
what the
got my
green
green
card
card.
is.
That's what I'm saying. So it was worth it,
And a
right?
piece of candy or a cookie on the way out. That's how we
I
do
got a
it. That's how
gold
we do it here.
star on my passport.
That's exactly why they're jumping over the fence, Ethan.
Yes.
Now you understand all the illegal immigration. So there's a lot of pressure to get
do you
in. It's
went
worth the fence.
by reading the accent accurately?
Yeah,
From
yeah, yeah. But I'm down under, so we've
Australia,
actually had to
okay.
turn the camera upside down so I can be the same way as you guys right now.
That's exactly right. Ethan's hanging upside down from the ceiling this morning. It's what, 10 in the morning there?
Yeah, 10. Oh no,
10.
11.
Is
No,
it
it
11?
is 10. No, it is 10. None of the clocks here are right. Remember how I told you I'm right on the border? So
Right. Yeah, that's
yeah,
right.
sorry.
His city splits the time zone. We just barely switched our time zone last Sunday. So,
Mhm.
so yeah. And nice. Let me kick us off real quick. Welcome to the conversation where we unpack the wild, interconnected chaos shaping our world, including the population's decline and all the reasons for it. Today's guest is Dr. David Hatch, a research professor at the University of Texas Austin's Institute of Fusion Studies. Hatch focuses on nonlinear plasma dynamics using high-performance computing to model and optimize turbulent transport and fusion devices. He pioneers gyrokinetic simulations and edge transport barriers critical to fusion energy viability while fundamentally exploring kinetic plasma turbulence in high-dimensional phase space. Dr. Hatch, appreciate you joining us today. And I imagine we are going to spend a lot of time trying to figure out the last two sentences of what I just said.
I think I can see it in my mind. It's like a tube with plasma, like, doing all this stuff, right? Sure.
Well, this week's conversation was your pick, Ethan. Why don't you kick us off on what this conversation is and what we're talking about in nuclear?
Yeah, well, so like, I don't know. I feel like one of the main real causes of any kind of economic growth or population growth or civilization is having energy and power. And I feel like we solved that problem a while ago. And it seems to me now that it's more of a manufactured problem that we don't have enough power to run the planet. And I mean, I think the answer, half a century ago was nuclear. And we can go into reasons why we haven't explored that as much as we should have. And it's great that you got David on because, that's the next step, right, is fission. And hopefully David will be able to tell us how close we are to that. But even nuclear aside, technology is the new energy. Commodities was the energy of the old world, just like print was a commodity. Like the print was how you stored data in the old world. I guess everything's gone digital, and I can see now, instead of countries fighting over gas resources and, all that kind of stuff, I could see we're on a trajectory right now where we're going to have energy abundance based on technology, which is it's not even, it's unrenewable, right? Like, oh, no, sorry, no, it's renewable. It's unlimited. It's not a resource anymore. But
I
anyway,
did find out
I just
University of Texas has a nuclear power plant, right?
Well, and so I don't know. And that's the other question is, why did we stop building nuclear power plants? I live in Australia where we don't have any nuclear energy. We're hoping to go that way with some kind of agreements we've recently made with America with trying to get some nuclear powered submarines. But there is a combined international effort right now with all the countries in the world trying to solve fission in France, I think, as well. And it sounds like it's getting close, like 2030. But even still, in the meantime, the nuclear energy we had was the cleanest. Like it was the cleanest source of energy that we were creating, or that we are creating still today. When you compare it to coal, oil, and gas, they're putting in hundreds of, millions of tons or something. And I know nuclear energy only amounts for a small portion, but it's significantly better for the environment. And yet we can't have it as a power plant in the middle of nowhere, but we could put it on mini submarines and send them around the world. We could put nuclear reactors in an American submarine that'll last 100 years or something. It's just insane. And then even the French now have got a mini sub where they're putting in these mini reactors that are like 10-year nuclear subs. It's like if they're safe enough to put in a military combat environment where they're going to be dodging torpedoes and bullets, then why can't we have them in a safe city, where we can get power from? That's my questions.
Yeah, there has been a bit of a turn. It seems like we have continuously made weapons, but we have only put in 2 new reactors in the U.S. in the last 40 years. So, yeah, both in Alabama. I guess, Dr. Hatch, what got you into this? Everybody sees it as or I would say it's slightly changed recently, but for a while it's been seen as a bit of a dirty energy.
Yeah, in fact, it's interesting. I was a postdoc in Germany for 2 years during the time period when Fukushima happened, and the Green Party became extremely opposed to nuclear energy, and Germany committed to phase out all their nuclear power.
And they now have, right?
The result of this was bringing online even more coal, and not just any coal, but the dirtiest kind of coal. So yeah, I totally agree that the world should have more nuclear. It should be streamlined. It should be much more cost efficient than it is right now. A lot of the opposition, I think, is irrational and can be handled with innovation and with new technologies. Just a few caveats right off the bat. I'm a fusion physicist, and there is a fairly big gap between nuclear fusion community and nuclear fission community. So I would say I'm literate about a lot of the nuclear fission issues and the state of things in nuclear fission, but that's it. I don't consider myself a real expert on those topics. So I can, shoot the breeze on those topics, but really fusion is where my true expertise.
So do the fission people have to be on a whole different side of campus? Is that where you?
They do, yeah, they are actually. Yeah, there's very little crossover.
Do they put you all in pretend offices where they're like, sure, the hoped for office? It's like one day we'll get you.
Do you both have a football team? Do you both have a football team?
So yeah, you're talking about the fission reactor on campus. That's on Pickle campus. It's an educational, test reactor. There used to be a fusion reactor. I mean, what you might call a
really?
reactor back in the 90s. Not really a reactor, but a plasma, fusion experiment. But that was phased out. The major one was phased out in the 90s as experiments had to become bigger and bigger to be relevant. They consolidated into a few major labs across the U.S. And so now people here collaborate on different experiments around the U.S. and the world, working on fusion.
And even the White House. I mean, there was a slight movement under the Biden administration, but more recently by executive order under the Trump administration, they've really made a big push to kind of support. I would say more uranium enriching here in the United States. And do you find that, what they've done with Halia and what is it? I forget what it's called, the FRDR, whatever, the one for weapons grade uranium. Do you find that puts any extra momentum into fusion?
Oh, really? The fusion and fission enterprises are really almost entirely
That's separate.
Yeah. I do think generally there can and should be a lot of I think a more favorable environment for fission also is somewhat more favorable for fusion, but they're really in completely different categories. Fission has been around for, it's been producing energy for what, 80 years now, 70, 80 years now.
And the dream of fusion
I'll-
is that it's not going to be as dangerous too, right? So that's probably why you probably wouldn't even have the same kind of stigma associated with your side of campus as you would with the fission guys that are just can't seem to keep their nuclear power plants from melting down.
Well, actually, I think
Mr. Burns.
that's a bum rap too. Actually, I think the state.
I know. I'm sorry. I'm a devil's advocate most of the time. Sorry, I don't take anything I say seriously.
Yeah, I mean, there's Fukushima, there's 3 Mile Island, there's Chernobyl, of course. Chernobyl was by far the worst of those, but if you add up the deaths and the hazard from all of those combined, it's still a fraction of the damage that that coal does, not just from pollution, but from also just not just from climate change, but
Even
also
just mining.
pollution in the environment, health hazards of pollution in the atmosphere. But yes, one of the advantages there are a couple of really key advantages of fusion over fission. One is that it's much safer. There's zero risk of the sort of meltdown, runaway reaction that you have in fission reactors. It's so hard to do that if anything goes wrong, the material will just dissipate. There could be a very localized, explosion sort of thing, but nothing that's going to be a hazard for anything beyond, the immediate environment of the reactor. That and the fuel is basically inexhaustible and not weapons applicable whatsoever. The fuel is there's different fuel cycles, but the main one is deuterium, tritium. These are different isotopes of hydrogen. You can get deuterium from any source of water just by filtering out this isotope from any water source, including ocean water. Tritium is more difficult, but it comes from, you can breed it from lithium. And until batteries came along, lithium was, much less of a hot commodity. But even with batteries demanding a lot of lithium, there's still enormous reserves of lithium, and this could fuel a fusion economy for centuries. There are other fuel cycles that don't need the lithium to breed tritium. So bottom line, the fuel source for fusion is available, is basically inexhaustible, almost negligible cost in comparison with everything else, the balance of plant, everything else that goes into a power plant. And most of the deuterium part is available anywhere in the world. There's no geopolitical implications for the deuterium fuel source. Lithium, there are places that have more or less lithium, but also widely available. So the fuel, and it's so energy dense that you can produce vast amounts of energy with just the tiny amount of this fuel. So that's really the benefits of fusion. There is very low level, it is a nuclear process, but very low levels of nuclear waste, low levels of radioactivity. There is some, but if we didn't have nuclear fission kind of conditioning us, this knee-jerk reaction to radioactivity, it would be really a non-issue. Those are really the two selling points in relation to fission, and a lot of other energy sources. No carbon, zero carbon, very little radioactive waste, and virtually limitless and very affordable fuel. The main challenge is it's just extremely hard to make the reaction work. And right now we are in the current state of the technology is that we can get out about as much energy from the reaction as we put into it. There's a whole slew of different concepts in various stages of development that are really trying to break that barrier and produce much more energy, high fusion gain, much more energy than is used to initiate the reaction. But those are all, as of now, in development.
you brought up a couple of things. One, I think security and the environmental impact. Security-wise, I looked up on the fission side. The United States, we produce about 20% of our power comes from fission reactors. From about 97, I saw reactors throughout the U.S. We haven't, like I said, we've only put up a couple of new ones recently. However, the uranium-235 that we use to do that refined, 0% of that is refined here in the U.S. and by U.S. companies. Oddly enough, we buy most of it from Russia. So to get that to fuel our reactors, we have to get from Russia. It's about 5%. And then to get into the safer type stuff, we're trying to get about 20% refined. And that exclusively comes from Russia and China. And so to your point on security measures, it is, we're limited on how we can really advance this power based on who has it. Whereas tritium, we can really get this in a much larger supply. And it takes, I think on the environmental side, there are estimates that all the spent fuel that we have fills up about a half of an Olympic-sized pool, held in about 70 different locations, usually near the nuclear reactors themselves. And so if you put that together, all the fuel we need for fusion is held in like a small water bottle.
But even with the waste too, they end up using the waste in the next generation of power plant, or they had been, right? So,
well, half-life of uranium-235 is what, 700 million years, something like that. So I mean, it'll go away eventually.
Back to your point about
byproducts are the ones that really are long-lived and very hazardous. But yeah, there are strategies for recycling this. In fact, fusion, that's one possible application of fusion, is as a neutron source for recycling nuclear waste from fission. In fact, I have colleagues here in the physics department that have they have patents on a concept like this.
And that's not like TerraPower or the X Energy that it's using it to do it. This is actually taking it to create fusion versus a new fission reactor with spent fuel, right?
Yeah, it would be the application would be using a fusion reactor to produce using the neutron from a fusion reactor to recycle waste from a fission reactor, from like a light water reactor. These very hazardous. Just what you're talking about, the swimming pool full of waste from our fleet of light water reactors across the U.S.
Because part of fusion, you have to actually like contaminate what you're working with something that's radioactive, right? Is that how you use it?
So
to create the plasma or whatever.
Yeah. So so maybe I'll just give you a quick overview of.
Don't you have the high button on your microwave, Ethan? It's pretty straightforward. Just
the major fusion concepts. There's two main categories. One is inertial confinement. The other is magnetic confinement. Inertial confinement, the main concept is zapping a pellet with the enormous lasers, and then just using just the speed of the laser. Inputting the energy on the fuel is fast enough to confine. The reaction happens before the pellet explodes. Basically, that's inertial confinement. Livermore, the big announcement from Livermore at the National Ignition Facility is in that category from 2 years ago. I think it was late 2023 when that, or early 2023, I think, when that happened. And the other category is magnetic confinement. That's what I work on. And the main concept there is the tokamak. It's a toroidal device, and it uses massive magnetic fields to confine a plasma in basically steady state, usually steady state. So it's not a pulse where you have an implosion and a fusion reaction like that. It's more of a steady state concept. And there's different concepts. There's the tokamak, there's the stellarator. There are field reverse configurations. There's different flavors of magnetic confinement.
Now, if we can break in there, because really what confinement is we've figured out how to create this fusion. We're basically reproducing the heat on the sun, right? Which is
like 1 billion degrees,
15 million degrees or something. But really, it's how do we hold it? You can't, it's confining this and being able to harness this is the problem, where it melts everything down. You have no fission. So you spend a whole bunch of energy basically to melt everything. Well, I imagine it's every kid's dream job to like just
Blowtorch
they're paying you a bunch of money,
something?
just like ultimately we know it's going to burn down, but how can you burn it down? But the objective here is to try to ultimately have something that can manage to hold this heat. Is that correct?
Yeah, that's right. So if we take the tokamak, for example, there are 3 parameters that you need the product of 3 parameters. So there's the density, the temperature, and what's called the confinement time. The confinement time is basically if you heat up the plasma to a certain temperature, how long would it take for that heat to leak out? And you need to optimize these so that the product of these surpasses a certain threshold. And like you said, the confinement is the big issue, and the plasma has to be heated up to optimally something around 10 times the temperature of the core of the sun. The sun manages this just because it is so massive that gravity keeps everything together. And, but you can't do that.
This is definitely burnt popcorn. So.
Yeah, you don't want to put anything you want to keep, you can't put in there. In fact, that's one of the challenges for actually understanding what's happening in there. You can't stick any probe.
No
Can't
probes.
You need,
there's no Teflon glove in there, Ethan. So
exactly.
Yeah.
If you want a funny anecdote, I was just visiting a reactor in the UK, and they measure they use spectroscopy to measure what's actually in their plasma, and they say after they do maintenance on the plasma, there's always sodium chloride that shows up as a signature. In other words, sweat from the people working on the reactor. Literally, they could pick that out of the spectroscopy from the plasma. But so the trick is confining this, because you can't have anything that's 10 times the temperature of the sun touching the material surfaces. So you need it to be extremely hot in the central part of the plasma, and then it has to be cool enough at the material surfaces that either one of 2 things is going to happen. It's either going to melt the material surfaces, and those impurities will get back in and destroy the plasma, or it will just destroy the material surfaces, and you no longer have a confinement device. And so magnetic fields are extremely effective in doing this. Even right now we have plasmas that can get up to 10, 20 times the temperature of the core of the sun. Do this reliably. And then at the actual surfaces that hit the materials, it's more on the level of something you'd have in a neon light bulb. So we can do that. The trick is doing that and having sufficiently high density and sufficiently high confinement time so that you get a net energy reaction. And right now we're at the stage where we can get out about as much energy from the reaction as the energy you put in to initiate it. But we need to take that next step, and that's what the next generation of devices are designed to do. I'm optimistic that will happen in the next few, a very good chance it'll happen in the next few years. I'd be very surprised if it doesn't happen in the next, say, 10 years, 10 or 15 years.
Well, just so I understand it right, basically you're using, superconductor magnets. The plasma is being repelled, so it's basically a non-frictional surface. It's basically hovering there for as long. Is that correct?
The magnets, the way it controls the plasma, a plasma is just a gas where if you think of the air around us, each particle, each atom in the air, mostly nitrogen and oxygen in our atmosphere, the electrons are attached to the positively charged nucleus of the atom. In a plasma, it's so hot that the electrons are no longer attached to the nuclei. And so it's really, instead of one neutral gas, you can think of it as 2 charged gases. One gas that's made up of the nuclei or the ions of the plasma. The other gas is the electrons. And so it's a gas that has all the complexity of the gases that we're familiar with from air and water. So anything turbulent, if you imagine, flying a plane being in a plane where you're experiencing turbulence and this really chaotic motion, complex chaotic motion from conventional gases and fluids. And then you add the complexity of these fluids being made up of charged particles. So they also react to magnetic fields and electric fields. That's what's going on in one of these fusion devices. And the reason that magnetic fields confine the plasma is because, I don't know how much physics you've had, but even in an introductory physics class, the sort of thing you learn is the motion of a charged particle in a magnetic field. So if you think of a magnetic field line, a charged particle feels no force from the magnetic field if it's traveling parallel to the magnetic field line. But if it's going perpendicular to the magnetic field line, it will have this helical motion around the magnetic field line. So if you have really strong magnetic fields, then this gas of charged particles, the particles they're perfectly free to stream along the magnetic field. And in a torus, that's the topology where you can have these field lines going forever, and they cycle back on themselves, and you don't have to have any of these field lines that actually escape this device. And so the simplest model is simply that the charged particles follow the field lines around forever and ever. And if they try to go perpendicular to the field lines, the magnetic force keeps them spiraling around the magnetic field instead of escaping the device. That's the simplest picture, is this picture of charged particles around magnetic field lines. But in reality, there's a lot of collective behavior. So the charged particles work together to create their own magnetic and electric fields, and it's a mess of instabilities and turbulence and chaotic motion. And so that's what I do. That's my area of expertise with understanding
It sounds like you're either going to accidentally discover time travel or create the Hulk.
Well, I think it's no coincidence that there is a lot of this in science fiction, and the Doc Ock in I think that's a Batman movie, right? Or is that Spider-Man?
Spider-Man. I think I think it's Spider-Man, maybe.
Yeah, I think you're right.
Anyway.
Doc Ock and Spider-Man, and then Iron Man. His reactor looks very similar to what you might think of a Hollywood version of a tokamak. So it does kind of spark the imagination. That's true.
Well, before we jump into more on the tokamak, can we jump back to maybe the other competing models of basically trying to cool this? Because as I understand it, there's one where it's a cooling barrier, and this reminds me of basically a home air conditioner system, that it's literally taking the heat inside, it's running it through coils, and those coils go outside and try to cool it off. Is that right? It's not the most popular, but they're trying to cool the outer walls. Is that how that works?
So I'm not quite following what concept.
I looked at one, and there was a cooling barrier, and it looks like it's not too widely used. But I think
there's one where you could blow on it. Like when you get a really hot fry, and you just blow on it for a little bit, or you put it out the window in the car while you're driving.
There's
in
four
general,
Ethans there.
You're both getting at one of the really key issues for magnetic confinement. You're going to be producing. So the next generation fusion devices are they're going to be producing at least hundreds of megawatts of something in the range of hundreds of megawatts of steady state power. And so in the deuterium tritium reaction, 4/5 of this goes out through neutrons that pass through their neutral, so they ignore the magnetic field, and they go out and they're captured by a blanket, and they fuel actually the thermal cycle that creates electricity. But 1/5 of that energy is particles that are confined in the plasma, so they heat the plasma and keep it going, keep the reaction going. But it also has to be exhausted. And so the way you do that is incredibly challenging. So a reentry vehicle coming in, so from space, a reentry vehicle coming into the atmosphere is something on the order of, it's less than 10 megawatts per meter squared of heat flux on the device. and we're looking at least that, and probably more for next generation reactors. So just the exhaust handling of the heat exhaust from these reactors in the next generation reactors is an extreme challenge, and that's one of the areas that's most pressing areas of research for this next generation. It's kind of, once you get this amazing fusion reaction,
Once you get that ball running, you can't slow it down.
Yeah, that's right.
So is it more materials research that's needed now? Then is
yes, exactly. And I'm a co-founder on a startup company, ExoFusion, which is really innovating in this area, and we're developing novel liquid metal materials that are as plasma-facing components with optimal characteristics for handling the heat flux. And there are ways to do this that are, pretty straightforward and reliable to exhaust the heat, but then the connection between that and maintaining the confinement that gives you the fusion reaction is incredibly sensitive. There's trade-offs, a lot of things you'd like to do to handle the heat exhaust, damage the confinement, lots of things that you'd like to do to optimize the confinement, really make the heat exhaust more challenging. So that's a huge area of research for magnetic confinement right now. And that's a big focus of my group in the university and also our company ExoFusion. In fact, we have that's one area that's gotten a lot of momentum in terms of DOE grants into the company. We have 3 major grants to develop those liquid metal alloys as plasma facing components.
Any impacts you've seen in this last administration in regard to a lot of the DOE grants or any of the other research grants in regards to fusion?
Yeah, I mean, fusion is has the benefit that it's not really, it doesn't touch any of the really sensitive kind of polarizing issues and political issues.
We could all agree we need more power in the future.
Everyone's just hoping that fusion will work.
Yeah, I think it's kind of general bipartisan support, but I mean, it's also not big enough that there's any huge lobby for fusion on either side. I was actually part of a kind of a lobbying day for the fusion community, where several people from the fusion community went to Capitol Hill and met with staffers, and it was all, the responses we got were always favorable, but nobody was willing to take up the torch as a real champion of fusion energy, but everybody was.
Yeah, I imagine on Capitol Hill it's like the unicorn. Everybody loves to talk about it, but nobody's ever seen one.
I mean, there was no pushback. Everybody was on board. China, there's enormous enthusiasm and investment in fusion in China right now. They are quite a ways behind, and right now in terms of the state of their program, but they're catching up quick, and the amount of investment they're putting into it is enormous compared to what we're doing right now. Really,
they're still working with fission at scale too at the moment. So America's not building nuclear power plants, but China is.
Well, China's doubled the amount of its power. It's shooting to triple it, but in doubling it, most of it has been coal. So they've done a lot of fission, but a lot of coal. So,
well, even their weapons program, they are enriching so much uranium. They're buying it from us,
right?
And I think talking about Trump, I think he just did a deal to get about $400 billion worth of our uranium.
Well, Australia is one of the top producers for uranium, although they don't refine it. But yeah,
we send it to China. Yeah,
they don't have any nuclear power plants, but they make a lot of uranium. But let's jump into the tokamak and what did work. We now have the CEA's tokamak in France. They had it run for 22 minutes, which everywhere I've seen it, they counted by the seconds. And that's an industry that's used to counting seconds when they report it by the seconds, not the minutes. So I mean, could you walk us through kind of why this is a big accomplishment? How long it took them to get there, and what this will mean for you and really the rest of the industry as far as learning something from this.
So the duration of a discharge, minutes, seconds, whatever, it is a real, part of the challenge getting to the next step of having a viable energy source. But it's only part of it. Really, that's a different parameter than what I'm calling the confinement time, which is how hot you can get the plasma with a given amount of heating power. So they're kind of two separate things, and I think the confinement issue is actually more challenging than the steady state duration of the discharge.
So you're really waiting for them to fix that so you can get to your solution. It's like, hey, you guys, hold this for a
Well,
while, and then we'll help you get rid of the heat.
the reason why they can't have it on
actually.
for that long, the reason why they can't have it on for that long, Joe, is because there's nothing that can hold that, right? It's just gonna. So
There's
that's
a
why
few
his
reasons.
liquid metal's gonna solve that, right?
Yeah, actually, liquid metals would these liquid metal alloys would really be a benefit for a long duration operation, and also for confinement. Both of those things.
And
But
so,
for example,
what just with the metal, like how long would you be expecting that metal to last? Like, so how long, like indefinitely, or would it deteriorate at some degree? You know,
that's one reason why a liquid metal solution is really appealing, is because it's replenishable. So the other, probably the other alternative is tungsten, which is a super hard refractory metal that can handle high heat fluxes, and it's basically the toughest thing out there in terms of a conventional metal. And but even
Makes
that,
for great jewelry, really cheap.
have you ever actually held tungsten, or played around?
Yeah, it's the real heavy one, right? It's
It's
like very dense, right?
like you can have a little cube, like a dice size cube, and it's just shocking how heavy it is.
All right.
But it is even something as robust as tungsten under certain plasma conditions. If they're extreme enough, it'll wear away in a matter of minutes. And so a liquid metal is appealing because you can replenish it. If it wears away, you just replenish it as much as you need. There are, of course, challenges with liquid metals, engineering challenges, but it really does have advantages if we can get it to work. Yeah. So the other thing, I mean, just one other thing that limits the duration of discharges is simply things as simple as your power sources and your cooling systems. How long have you engineered them to last, right? So the experiments that are really pushing those parameters are really optimized to have those cooling systems in place to handle that. And some other experiments, in fact, the experiment that I'm most excited about is a tokamak that's being built by a private company, a spin-off from MIT called Commonwealth Fusion Systems. And it's not pushing the duration of a discharge. It's intentionally doing very short discharges. It's trying to maximize confinement and really trying to push parameters in terms of this fusion triple product and fusion gain. And their design is intended to demonstrate that you can get enormous amounts of fusion gain. So as a first step, a first year of operation, they're targeting just break even. So the equal fusion power production to the amount of power you're putting into the plasma. But then in subsequent years, fusion gain of 5 to 10 times as much energy out as you put in. And this device is currently being built in Massachusetts, suburban Boston area, and supposed to come in the next year or two and start producing results on that timescale. And so according to their timeline, they want to demonstrate high fusion gain before the end of the decade.
yes,
Wow.
2030.
Yeah, before 2030. Yeah.
And so would your solution be assisting in kind of the exhaust of that heat if they actually get that to work? Now they're going to have to figure out a way to manage the heat.
Yeah, so that's one reason they're only going for short discharges is because of the exhaust problem. And this is their stepping stone, their stepping stone towards a real reactor. This is not a fusion pilot plant. It's simply a demonstration device demonstrated that you can get the fusion gain you would need for a fusion pilot plant. There's a whole other set of challenges that go into an actual fusion pilot plant where you run this high duty cycle, steady state for months, years, with the whole thermal conversion cycle attached that is producing electricity. And a big challenge there will be exactly that, the exhaust challenge. So, and our concept is targeting exactly that sort of fusion pilot plant scenario. And we're hoping to get it in the conversation for some of these next generation fusion pilot plant designs.
And what are they? I mean, in fission, typically they're trying to heat something. Ultimately, you're heating it because you try to boil water, it creates steam, it turns a turbine. On another conversation, we actually found out the steam turbines aren't the most common. It was the gas turbines, which I found was interesting. The steam ones are actually made to cool the water because it gets too hot. So in your case, we're talking about temperatures so far beyond fission temperatures. Where does your company fit in this type of cooling, this exhaust that is coming out of here?
Yeah, so the entire reactor is not, in terms of cooling, is not the main issue. The number is, the really shocking number is 10 times the temperature of the core of the sun. Those apply only to the core of the plasma. By the time the plasma gets to the material surfaces, it's much cooler than that. And then it's really the heat flux, so the amount of power, the amount that you have to cool in a given time. That's the challenge. And then so for the first generation, most of these, not all of them, some of them have different fuel cycles, but the most mature and near-term accessible fuel cycle is this reaction, this deuterium-tritium reaction that produces neutrons. And then once you get the neutrons, the thermal conversion cycle is just think of anything else like coal, gas, nuclear. You're heating water and driving a turbine. So, I mean, there are different thermal conversion cycles that are more or less efficient, and these are all in the conversation for fusion reactors. But once you actually get the neutrons to heat up a blanket, then the rest of the technology is fairly familiar from everything that's out there and in the conversation for all these other thermal conversion sorts of power plants.
Gotcha. This is a great place to roast marshmallows by that time. You can bring it down.
Yeah. I mean, it's super hot, but it's nothing that's unfamiliar from gas or coal or fission plants.
Nice. Now, a lot of the money and research that's floating around fusion is somewhat limited. I see fission getting quite a bit. And now that it's been exposed that we really don't produce any of our own uranium-235, there's been a lot of money jump behind that to try to start companies to try to bring that on. On the fusion side, Bill Gates has his pet project. Jeff Bezos has a pet project. Musk has come out and really kind of been somewhat foreboding towards fusion in general. Do you see, what kind of money are we really and research are we going to have to get out there to put fusion really across the line to get there?
Yeah, that's a great question. So when I started out in this field about 20 years ago, there was really no private sector activity at all. It was all public sector funding. Over the years, the funding level, it's all funded through the Department of Energy, and it's somewhere on the scale of, $500 million a year, let's say, give or take. less than a billion, 500 million to $1 billion a year. And for a long time, the community has made different projections. How much investment would it take to really get fusion to work? And if you look at this on the scale of, say, a Manhattan project or an Apollo project, it's really pocket change. And so I'd say it's really impressive what the fusion community has been able to do on this. Sounds like a lot to some people,
Small budget
dollars a year, but really, compared to the scale of what we're trying to do, it's really pocket change. And so then we're in this situation where the public program is really underfunded to take that next step to commercial fusion. And we've kind of, everybody that's looked at it has kind of recognized that for quite a while. And so one strategy was, and this was the strategy that came out of the 90s, was to join forces internationally, pool resources, and have one big flagship experiment that would take the next step. And that's ITER.
And this is the whole world really coming
The
together.
whole world, it's really every developed country with a major,
Every nuclear
scientific.
power.
Yeah. So like South Korea, Russia, India, Japan, EU, and the US. I don't think I'm missing anybody, but that's the club. And it was kind of an inspiring agreement between Reagan and Gorbachev. Actually, it was initiated in the 80s. But then it became this mega project, very dysfunctional international collaboration, which has produced some good science, but it's been perennially behind schedule and over budget. And
They recently, just in the last few years, raised more money, right? From all
it
parties.
seems
involved.
like it's a bottomless, it's a blank check from most of the
Right.
government.
Is that why you can't get funding though? Because no one believes in it? Like you're always 2 or 3 years away, right?
Yeah, I think that's part of it. It's hard to catalyze really that political willpower if you have this perennial idea. The joke is that fusion is 30 years away and always will be. And this ITER project, I mean, I don't want to. There's a lot of good people working for it, a lot of good scientists, but it's 7 or 8 different countries contributing, not just pouring money into some central organization that has really the autonomy to make something happen. They're contributing in kind. So you're getting pieces of this vacuum vessel from the US, parts from China. They have to align with millimeter precision. Anyway, very, very challenging institution in which to do a huge project like this. And so the really inspiring and exciting development in the last 5 to 10 years is that the private sector is really getting involved in a big way, at least in terms of the scale of what's happening in the public sector. And so I would say most of the energy and excitement is now shifted to the private sector. The biggest one right now is Commonwealth Fusion Systems. That's a spinoff from MIT. But in the US, there are, I think, 3 that are on the billion plus level of investment, and say, 8 or 10 that are really building momentum and look like they have legs. And so not only does this diversify the number of concepts that we can explore, but it also just the private sector environment and incentives make things move much faster and much more dynamically. And the public sector is really, the US is really getting behind this, and a lot of the public sector, a lot of the DOE funded research program now is oriented around supporting the fusion companies doing research that aligns with their needs and interests. They are making enormous advances, but you just can't hire all the expertise internally in all these companies to close all the gaps. And so there's really it's being sorted out. There are, of course, roadblocks to these sorts of collaborations and agreements, but really much more engagement between scientists at labs and universities and the private sector companies, and the Department of Energy funding their scientists to work on aspects of the private sector fusion companies concepts.
So what do you think it's going to take ultimately? What line is going to be crossed where the masses come in? Because even though there's been some private money, we're really talking about the low billions. And nuclear is getting hundreds and hundreds of billions. And there's big companies moving lots of stuff in the fission world. So how, of course, if one of them were to get a reactor that was net positive and sustaining, of course, everybody's jumping in it. You just solve, the world's problems. But what is a minor thing that they're really going to have to get to the next hurdle in order to really get a lot of attention from the private world's in there, but we are talking about very wealthy benefactors, whereas most of the money is down the line where you see a lot of investors investing in companies that are now on the periphery of it. And, what do you think that thing is going to be that they have to be able to prove to kind of get everybody in there?
How do you make us believe?
Yeah.
Yeah. No, that's the most obvious thing is high fusion gain, right? Getting a lot more energy out of a fusion reaction than you put into it. It's not only just on the most boneheaded scientific level, but also a psychological level. That's what you have to demonstrate in order to catalyze the investment and everything else that you need to really take it to the market.
And that's what, 30 years away, right?
It was 30 years ago.
Well, if you ask me, this has been mostly a problem in the fusion community. So this big project ITER, I think, was really just the wrong path, and we could have done a lot of it even 20 years ago on a much smaller. I won't get into details. I could.
By that you mean if you would have had all those resources, including capital and scientists, you could have done it more efficient in a different way. Is that what you mean by
yes?
ITER being
that,
the
also,
one?
I mean, there are other technical paths to demonstrating high fusion gain that would have, instead of having a mission creep of sorts and trying to put too many things into one device, more targeted, smaller scale, smaller cost experiments that could have made some of the main.
Because ITER is one gigantic hole in the ground, right?
Oh, it's enormous.
Yeah, it's huge.
So one thing that I've learned to do in life is you promise a little and you over deliver.
This is Ethan's marital advice in life. All 6 of his wives have really appreciated.
Not at the same time.
Right.
Not a billion.
So I do think that the high fusion gain is, I think, very plausible in the next 3 to 5 years. And if it's not there in the next 10 years, I will be surprised and very disappointed. Not to, I want to give a very accurate, like you said, not oversell this. That's just the first step, and it's still a very large step from that.
Because that just proves they have a model of basically having net positive production. So now the next piece is they actually have to now continue with it, which would be a different version of the reactor, but one that could do it long term.
Yep.
And then of course now they have the exhaust problem.
That's steady state, and that's connected to all the other the balance of plant facilities that have the thermal conversion cycle that can the structural materials that can handle the neutron damage from a DT reaction long term. There are a whole other set of issues that to really make it commercially viable and making it a scale that's just cost competitive on the market. So all these things, nothing looks like a deal breaker to me, but they all need innovation. They all need investment. And a lot of that is instead of the plasma physics, which I, know and love, and I've been obsessing over in my career. A lot of the things that will be needed to make that last step to a commercially viable fusion reactor are a totally different area of expertise, fusion technology, engineering that's very distinct from the plasma physics that's getting you there in the first place. But yeah, I think the way you framed this is exactly right. We need some initial breakthroughs and demonstrations to catalyze the investment that's really needed to take that final step. And it's interesting that the initial reactor for CFS is called Spark. And let's see, I'm sure it is some acronym, I'm sure there's some private acronym that goes along with it. But really, psychologically, it's exactly what you put your finger on. This is intended to be the spark that really demonstrates fusion is up to the task and will catalyze the next level of investment to get us all the way there.
David, instead of asking it how far away, is it something, or is it possible that you could go into work one day and there is some kind of new piece to the puzzle that solves a massive problem, like the material, I guess, the side of. But is that always something that you guys live in the possibility of? Is that any day there could be something that gets you past a point or creates that spark?
That's a great question. And 15 years ago, I would have said it's very unlikely. But now in the current environment, there's this whole, portfolio of fusion experiments. And some of them are going back to concepts that were around, 40 years ago and were kind of cast on the wayside for what or another. But there's new innovations that have revived them. And those are the ones that are, in terms of, so I put things in two categories. One is the category of concepts that are very mature. We kind of know what we're going to get. And there's still a lot of innovation that can optimize those, but there's nothing, like you say, that we'll wake up tomorrow and say, hey, this new discovery is the new route to fusion. It's really, there will continue to be, really big innovations and breakthroughs there, but it'll be kind of more incremental towards a power plant. But there's another class of experiments and concepts that they're starting out farther behind, but they really are in the category that if they do pull it off, if they can pull it off, then they sidestep a lot of these issues that the mainline concepts have. They have the potential to be much cheaper. Their fuel cycles are much cleaner. They don't rely on a neutronic fuel cycle, which is messier, and you need this thermal conversion. You have issues with irradiation of your structural, neutron damage to your structural components of your plant. But they are farther behind. So it's much, that's the calculation the investors are making, is they know very well that these concepts are much farther behind, less developed. But if they work, they're more in the category of what you're proposing, something that you wake up tomorrow and like, oh wow, this actually works, and it revolutionizes everything. And it's way to go. It's clearly cheaper. It's a much shorter timeline to being commercially viable. So there are things out there. One, I'll give you a couple of examples. One is Zap Energy. This is a spin-off from the University of Washington. And
Spark and Zap.
Yeah. Zap is literally the very first, the simplest fusion concept you can imagine, the very first one that was ever proposed. You just have a column of plasma, just a cylinder, and you run a massive current down it and try to get it's called a Z-pinch, and you try to get a fusion reaction from that. And early on, it was abandoned because there were massive instabilities that just destroyed it. But then at the University of Washington, they realized that if you spin it really fast, so you're spinning this column of plasma, then you can stabilize some of these instabilities. And this concept really has legs again. And their first couple of demonstration devices really pushed the parameters on this concept really far, really just to the verge of break even. And they're currently operating a device that is supposed to be, they were selling it as being at that caliber where they could demonstrate something like fusion break even. So this is an example of one of these companies that's taking, I guess you'd say more of a primitive concept that's farther behind in development, but if they could pull it off, it would really be revolutionary. Another one is
Yeah,
called
because
it's also just a column of plasma, but here you're using big magnetic fields to kind of seal off the end of the bottle. Instead of having a torus where it wraps on itself, it's just a column, but we're using big magnets to seal. You can think of it as a leaky bottle, and the higher magnetic field you can get, you're kind of sealing the ends of that bottle. So there's a company at the University of Wisconsin that's pushing that. Another one that's spinning off from the University of Maryland, and it's another one that if they really, it's simple enough that if they really make a breakthrough, it could be revolutionary on a really fast time scale.
yeah,
There are
because
other
it sounds like what you.
or a little more
Sorry,
far
it just sounds like you're saying that a lot of the problems that you face, and the reason why it's always going to be 30 years, is because you've invested down a pathway, you've got it almost working, and so you think you just got to tweak it a little bit more at this end when maybe you've gone down the wrong process at the beginning, right? Maybe you've just been putting band-aids on things for the last 30 years, and those band-aids have been getting it closer, but maybe you haven't started in the right place. Is that what these other companies are doing?
Yeah, some of these other concepts were maybe abandoned prematurely, and there's been a lot of innovations that are giving them another kind of a second lease on life. Yeah, and so the tokamak track, it may, if you track that, so this fusion triple product, if you plot that over time, it's and you put it on a scale like say Moore's law, from semiconductors, it's actually surpassing Moore's law up until like the early 2000s. And then ITER was the next step device. It was delayed, it was over budget, and it stalled out.
And by that, you mean new technology is shorter
the
and
next
shorter
step just
time. It's coming up every 6 months. The other stuff's old.
Yeah. I mean, over the first half century of fusion research, the progress was incredibly rapid. But then it kind of stalled out once the next step device became so expensive that it went beyond what individual countries were willing to invest in.
And again, though, it could be that maybe as science we went down the wrong way because of our understanding at the time too, right? Maybe we tried to build the wrong device.
That's what your mother said when you were born, Ethan. Just that kind of thing.
No, she never wanted me.
She's like number two.
Yeah,
well, I mean, to Ethan's point and to the general. Oh, go ahead.
Yeah, I actually think the tokamak. I don't discount that it could be the route to commercially viable fusion. I think it's a good possibility. But if I were to put my money on something, on one device, I would put my money on the tokamak being the first one to show fusion gain, large fusion gain, but the one that actually eventually breaks in and really makes an impact on the energy, the power, electricity production worldwide. I'd bet on something else. Ultimately, being
like the one that 10 times is the one that's a 10x is going to be something else.
I think something else will be more reliable and or cheaper ultimately than a tokamak at producing fusion energy.
So to get to that ultimate other thing, a lot of the time technology and research follows the money. And Ethan and I, our entire show here is really about population decline and how things are changing. And so as we see, there are now the next generation, there are more of them than our generation, Gen X. However, there's a population decline. There's few of them. What are you seeing as far as the interest of jumping into this field from the next generation to really spark off that idea of creating new companies, creating new ideas, and trying to take this and really foment it into, broader and new advancements?
Yeah, I think I definitely have seen an uptick in interest from graduate students with the developments in the last 5 or 10 years with major major new companies, major new experiments in the private sector. It's really changed the environment and just the psychological environment for people getting into the field. A good case in point, I have a new graduate student right now. He's a second-year graduate student here at the University of Texas from Korea. And he came into the field interested in equal measure in the science and the entrepreneurial aspect of things. So he's been just voraciously getting up to speed on the physics and the technical aspects, but at the same time, he's going to entrepreneurship workshops and programs in the University of Texas. He's doing internships in private sector fusion companies, and really is driven by the intersection of both these things, the actual technical side of things and the prospect of pushing it forward in the private sector. So yeah, I think that's more and more common. There are also, young people coming to the field who are going through graduate school, and maybe the previous generation, they were hoping for a, nice cushy job at a national lab where you settle down and you're set for life. But a lot of the young people are saying, hey, I'm going to take the risk and roll the dice with a startup company and really embrace a much more dynamic but risky career path. So I think it is. They just psychologically, it's a much different environment now than it was 10, 15 years ago.
That's exciting to hear. Wrap us up and tell us a little bit more about your company, where people can find out more about it, where people can find out about you over the next 30 years, where they can find you.
The company is called ExoFusion. We're a small spin-off company from the University of Texas. We our business model is not typical in the fusion the fusion ecosystem. Most of the companies are vertically integrated, pushing forward one concept to a final path to a fusion reactor. Our business model is to support the entire ecosystem. So everything in the spectrum of magnetic confinement concepts is within our purview. We're hoping to contribute to all of these concepts and really make an impact wherever we can to pushing them.
And that really means you're reactor agnostic. I mean, they need your tool
we do
way.
have opinion. We think that certain things have better chance and brighter prospects than others. But yeah, really, we are eager and willing to work with concepts across the entire ecosystem, and some of the concepts that are a little farther behind in their development, we think our innovations can bring that into the category of really being viable for fusion gain. And the more mainline concepts like tokamak accelerators, our innovations can bring them from something that is clearly viable for fusion gain, but needs a lot of innovations to become reliable and cost-effective in the marketplace. And we have a portfolio of IP, a lot of simulation and modeling capabilities that are applicable across this whole spectrum. We've been building a lot of momentum in terms of funding. We have a small seed round already in hand for a couple of years, but that really just catalyzed getting off the ground. And since then, we've been pretty self-sustaining with subcontracts from different labs and companies, and also DOE grants. One of the main things we've been that's built a lot of momentum is this novel liquid metal alloy concept for plasma-facing materials. It has we have a grant, NFUSE grant, ARPA-E grant, and a FIRE grant for this. It's really building up a lot of momentum in the community and a lot of interest in the private sector also.
Have you been approached by Cyberdyne? What's one who made the Terminator? I just they've got an interest in. No, sorry, it sounds cool.
Those are the movie rights.
Yeah, I just think it's awesome that we are living in a time where a lot of things that it's the belief thing, right? We're getting so close to these things which we've been able to
Easton
understand
used to think it
in
was like
theory
30
for so
years
long.
away. But
So liquid, I love it.
this has been great. Really appreciate it, David. Thanks for joining us. I think this is a fascinating topic as we see electricity, with AI and what's happening. I mean, it's going to be a force to reckon with in the future. And there's so many different things that so much money is going after fission. But fusion really has been one of those that I think in regards of money, research, and focus, it really has been neglected in regards to the impact it ultimately can have on the entire world. So definitely one we wanted to, give a highlight here. So really appreciate you joining us today.
Great to chat with you guys. Thanks a lot.